All right, so we're going to switch and look at things, I think, from a different point of view. That was taking a look at biological systems, which then create electrical signals and result in mechanical motion. We're going to look at mechanical devices to create electrical signals that maybe then are used to model biological systems. But the first speaker in this session is Professor Jun-Bo Yoon from KAIST. He has a background in electrical engineering. His degree is from KAIST, with a postdoc at University of Michigan, which I won't forget to mention because it's one of my alma maters as well, in which he created the first movable dielectric tunable RF MEMS capacitor. And he is a very prodigious author of numerous publications and patents in this field, has worked in MEMS for 20 years now, and he is going to give a summary talk on what we have learned when moving from the micro to the nano scale in electrical mechanical switches.
Okay, thank you, Ms. Chairwoman. So, good afternoon. I'm Jun-Bo Yoon from KAIST, Korea. So today I would like to take this opportunity to look back what the researchers have done in the microelectromechanical switches and see if we can apply those lessons from the MEM switches to the solving some problems in the NEM switches. So this is a conceptual view of the MEM switch. So if you apply the voltage between these two, then it exerts an electrostatic force, which is attractive, then eventually make the contact in the contact region. And this is what you can see in the conventional transistor. You know that this finite subthreshold slope comes from the fact that the current increases exponentially depending on the energy barrier lowering. But this hinders the further reduction of the threshold voltage. And this can be solved by the electromechanical switches because it can give you the abrupt switching. So we need more than the exponential growth. And these are all the beauties that we can achieve from these electromechanical switches, but the reality is not that good. And during preparing this presentation material, my PhD student, Ko, spread all the previous data into this framework. And it comes from the macro scale size switch all the way down to the nanoscale switch. And the macro scale switches, we have already a commercially available product, but not in the nanoscale switches. And the important thing we can learn from this graph is that size matters. So in a given device volume, it can limit the lifetime multiplied by the current figure of merit. So let's find out how we can improve this characteristic. So here shows a 3-terminal nanoelectromechanical switch that we made in 2009. The material was tinitride, and even it has a 20 nanometer gap here and 30 to 40 nanometer gap here, but still we have over 10 volt turn-on voltage. So it's very difficult to solve this high actuation voltage problem, and also the reliability. You can see that it's just 10 times. So in this presentation, I would like to review how we solved these problems in the microelectromechanical switches and find some lessons from the MEM switch and look at the differences between the MEM and the NEM switches. And then I would like to introduce some 3 approaches. One is to apply the lessons learned from the MEM switches, and another 2 are using some superior materials or the devising some new mechanisms. So let's find out why the high actuation voltage is the problem in the MEM switch. So this is the pull-in voltage, which is beyond this voltage, the structure collapses to the bottom. And this turn-on voltage depends on the spring constant and the initial gap. So in order to reduce the actuation voltage, to decreasing the spring constant and the decreasing gap is good. But however, if we do that, there might be some permanent adhesion, which is called as a stiction, happens because of the lot of nanoscale forces. So in order to prevent this phenomenon, there are some couple of solutions. So using a detaching electrode, or introducing a pre-charged or pre-biased electrode, or using some smart structures. So first one is the detaching electrode. So in order to detach from the electrode stuck to the bottom, we can apply the voltage in the other electrode. This is very similar to the seesaw structure. By using this mechanism, we can get down to the 3 volt, or we can make some levitation plate using the levering structure. Because you know the electrostatic force, we always have an attractive force. It is very hard to achieve a repelling force in the electrostatic actuation. So instead of that, we use the levering structure to intentionally detach a plate which was stuck to the substrate. So using this technique, even the dead switch revived from the dead status, so we can increase the lifetime to 10 times using this mechanism. Or we can use the pre-charged electrode. This is actually the same with the flash memory. So we are using the floating gate and applying some charges, then we can change the threshold voltage. That's the same. So using this technique, we can reduce the pull-in voltage from over 60 volt to the as low as 3 volt. The problem is to how long we can maintain this charge in this electrode. And the second method, which was developed by Professor King Liu in UC Berkeley, they are using the 4-terminal device, and they are using the body bias. This is very similar to the body bias in the MOSFET. So they succeeded to get down to the very small voltage using this method. And the third one is to use the variable spring constant. This is the normal cantilever switch. And the reason why we need a large gap is to increase the restoring force, because the restoring force is the spring force, which is proportional to the displacement. So in order to get the large enough restoring force to detach some stuck electrode, we need a high enough gap. That makes the high turn-on voltage. So the conventional case is to use just a single spring system. But if we make some smart structure that if the electrode pulls down to some certain level, and after that we can actuate the second spring, which has a higher spring constant, then we can achieve a lower gap as well as the high restoring force. So these are 2 examples. So the first one is coming from the UC San Diego, Professor Rebe's group. And the second one is from my group. So this cantilever, once the tip is touched down to the dielectric layer, then the spring constant will be changed. So we can use the second spring here, which is a very high, has very high spring constant here. And the second one, the entire source plate actually have 2 types of springs. The first one is the normal springs to handle the whole suspended source plate. But you can see that there is another spring here, which has beam structures. So once the dimple touches down to the bottom drain, then this beam spring actuated. So these are another example of to make some smart structure to have a second type of a spring. So the second problem of the MEM switch is the poor lifetime. And this is very complicated problem because there are multi-physics involved in this contact region. And you know that the electrical contact governs the lifetime of the switch. So these are the conventional failure mechanisms. So there are welding problem and material transfer problem, wear, and the micro-arcing. And also, we need to know that the real contact area is different from the apparent contact area. Actually, this is very small portion of the apparent contact area. So we have to actually increase the real contact area, or we can think about the refreshing the real contact area, or we can use some different material, or we can do the stress engineering methods. So first one is to increase the real contact area. This is the fundamental equation governs the contact resistance. So in order to increase the contact resistance, which means that in order to increase the real contact area, we need to lower down the hardness of the substrate, or we need to increase the contact force. So we devised some structure that instead of placing the gate and the drain electrode in the same plane, we put some gate electrode under the drain electrode. And we apply the voltage between the gate and the suspended structure. Then the electrostatic force actually penetrates this drain electrode to pull down this source plate. And by using this structure, we can enhance the contact force, because this structure can effectively pull down this source electrode. And also we use the soft insulating layer, which is the BCB, to increase the real contact area. Another approach is to use the second spring that I already showed you. And so this one can actually increase the real contact area as well, because these two are the drain split structure. So each drain has its own drain electrodes, and this is the conventional single spring system, and this is has the second two-step spring systems. You see that we don't know which drain electrodes have a successful contact, because each drain electrodes have different contact voltage, whereas these two-step spring systems can effectively pull down this suspended source plate even after the first contact is made, so that we can achieve a very uniform and nice contact, all these in these entire drain electrodes. So in this way, we can increase the real contact area. And the second approach is that we can use some new contact spots, so by using this actuation mechanisms. So once some spot is failed, and we can move to the left and right to find some new colony, new contact spots. Then in this way, we can use very large areas of real contact area to increase the lifetime. So this is a very nice example to enhance the lifetime using the enhancing the real contact area. And another approach is to spread some nanoparticles that after repeating the contact and detaching, the nanoparticles can move, so that it makes the new contact spots in every times. So by this method, they can increase the lifetime. So, and another approach is to use some different contact material. As we know, the gold is the famous material that can give you very low contact resistance. However, it is soft, so that the lifetime is not good. Whereas some researchers have been using the platinum or ruthenium, which are the hard material, that can give you a very long lifetime, but it has a higher contact resistance. So which one is better, soft material or hard material? Actually, we can use both. So this structure utilizes both materials, gold and the platinum, in the same single switch. So by using the zipping actuation mechanism of the cantilever, first the platinum part made a contact. And this can enhance the high harsh conditions, just like arcing phenomenon. And then after making this contact, then the gold part made a contact. Then all the currents can go through this gold contact. So this can take advantage of both the soft material and the hard material, so that we can maintain the low resistance as well as a longer lifetime. And another approach to enhance the lifetime is the stress managing. So for example, we can shape the gate signal to suppress the bouncing, or we can use the heat sink insulator. You know that the electrical contact generates the heating, and we usually use the oxide in the insulating layer. However, if we change it with the silicon nitride, which has a 30 times higher thermal conductivity, then we can reduce down the contact temperature so that we can prolong the lifetime of the switch. Or we can use the drain capacitance to prevent any arc comes from the difference between the voltage difference between the source and the drain electrodes. So these are all the methods to enhance the high actuation voltage and the poor lifetime of the MEM switch. So, but we have to note that the real electrical contact is made actually in a nanoscale. So we have to be careful about any nano physics involved in the contact area. And also we need to know that the apparent contact area is not the same with the real contact area. So in general, ideas from the MEM switch can be applied to NEM switches since they share the basic structure of the electromechanical switch, something like cantilever switches. However, the NEM switches can be operating in some other, under the other physics, which is the nano-based physics. So let's find out what is the difference between the micro switch and the nano switch. Actually, the most important one is it is very difficult to make the nanoscale electromechanical switch. So that's the number one. And also, sometimes we have to use the structural material, which is the same as contact material. And also, because the gap is already in the nanoscale, we need to understand why the van der Waals force is increasing and the adhesion force is ineffective over the entire surface. And also, in the contact region, it is already in the atomic scale. So contact force is very small, and contact area is also very small. Number of atoms are very small, and it is very sensitive to the alien films, such as hydrocarbon and oxidation. So I'd like to show you three approaches. So these are the table that I summarized all the techniques that we already used in the MEM switches, and then see if we can use that techniques into the NEM switches. And red one is already applied to the NEM switch. Blue ones it is possible to use in the NEM switch as well. However, the black ones are, I have no idea yet. So detaching electrode is already done in the nanoscale, just like a planar design or the vertical design. And one thing is that we can use the extremely small gap in the contact area. This is a normal two-plate system, and this is just like a pipe clip system. And we have a very small gap here, but this can govern the actuation. That's what we found in this typical unique structure. So electric field is confined in this local area that can produce a large enough force to actuate this beam. And also the contact area is very tiny, so we can suppress the adhesion force. So we don't need any detaching electrode. So this is what we've done. So 4 nanometer air gap was achieved. So by using this tiny gap, we achieved 400 millivolt. This is the world's smallest actuation voltage in the electrostatic NEM switch. But the lifetime is still around 10 cycles. Or we can use the insulating liquid. So we can put these nanoelectromechanical switches into the liquid. Then we can reduce down the actuation voltage, as well as we can increase the lifetime. So that's another method. Or we can use some new materials, which is carbon-based materials, carbon nanotube, and the graphene or silicon carbide. These materials can prolong the lifetime of the NEM switches. Or totally new mechanism is also possible and interesting. I know this work will be presented in this symposium. So molecular thin film can be used as to induce some tunneling current when the two plates are having the smaller gap. Or actually, we used a very thin oxide to induce some tunneling instead of just the direct contact to increase the lifetime. Or nano protrusion phenomenon has been used to make the mechanical switch, but this is limited to the two-terminal structure. So let me summarize the NEM switches. So ideas from the MEM switch are currently being applied to the NEM switches. So carbon families is very promising. And also, we can find out some new mechanism in the nanoscale switches. So fundamental understanding and the fabrication innovations are strongly required in these approaches. So let me conclude my talk. So we have looked at the two major problems in the MEM switches, high actuation voltage and the poor reliabilities. And we looked at some methods to increase these two problems in the MEM switches. So we got some lessons, and we see if we can apply the lessons to the NEM switches, and we found out what is the difference between the MEMS and the NEM switches. And I introduced to you a couple of approaches already applied in the NEM switches. But I can tell you that the NEM switch, nanoelectromechanical switch, is the area where still a lot of things are not explored. So with that, I'd like to conclude my talk. Thank you very much.
I'd like to start with one question. You mentioned briefly the effects of Joule heating, especially as you scale down to nano contacts, which may be a fraction of what you're intending. Can you talk a little more about the effects that the Joule heating has on the electrodes?
Oh, yeah, that's a good question. So actually, a lot of problems are made in the contact area. That's coming from the much portion of the problem comes from the Joule heating. And the contact, if the contact resistance is high, then Joule heating is more severe. Then it can increase the contact resistance further. So it's a positive feedback. So it can kill the device eventually. So that's the problem of the Joule heating. So in order to prevent that, we need to use the low resistance contact material or high contact force, and etc.
Okay. So I think the application where the nanomechanical switches seem like a perfect match is the Internet of Things, and in particular to do digital pre-processing before these devices, the sensors that scavenge power, before they transmit their radio signals, they do some digital pre-processing. And so it's very important to have zero leakage, zero standby power, and so forth. So we're not worried about heating in that application. But it looks like the degree to which we're going to have sensors all over the place, it could very well be that some pre-processing using nanomechanical switches would be very important. Now, but it wasn't clear to me how low a voltage do you think it's possible to get? I think you showed a slide with 0.4 of a volt, and there might be others that are lower. What do you think?
I think sub 1 volt will be possible, because I already demonstrated in the 400 millivolt, but I already showed you that there is some technique to reduce down the actuation voltage, just like this one, the pre-charged or the pre-bias electrode. So this method can enormously reduce down the turn-on voltage, even from the 60 volt to the 3 volt. So if we have a 3 volt device like the one that I showed you, then we can achieve below the 1 volt. And actually, in the sensor network, I think that the nanoelectromechanical switch, before applying the nanoelectromechanical switch, microelectromechanical switch is the more appropriate version of the switch in the IoT, because we have to deal with some finite amount of current by means of scavenging the energy or some other methods.
Right. I think you can get by probably with very little current, but you have to keep the voltage low.
Yeah.
And also, you need a great many. You need about 2,000 switches to do interesting digital pre-processing.
I see. Okay.
Any other questions? Well, let's thank our speaker again.